Hello, everybody. How are we doing tonight? Hey, Darian, how's it going? Hey, great, great. All right, well, let's go ahead and get this started. Let's see. Hey, Cassie. All right, so our last lecture was about an hour long, and my goal for these things is to keep them under an hour. So we'll just play it by ear. If you guys have any questions, feel free to ask them anytime. Like I mentioned before, I have a second monitor. Now it's over to my right, and I can't see it without turning my head, but I will periodically look over to see what you guys are asking or talking about. All right, so we can begin tonight by talking about macromolecules. Our lecture title for the night is What Cells Are Made Of, or What Are You Made Of? And if you've watched the videos in the learning unit that I put up yesterday, you can see that the macromolecules that we're interested in, the big molecules that we're interested in, are divided into the same categories as the components of the food we eat. So, for instance, we have here carbohydrates, proteins, lipids, and then also nucleic acids. Now, if you've ever looked at a nutritional label, you'll see, of course, carbohydrates, proteins, and lipids listed, and you typically won't see nucleic acids listed. The reason for that is that nucleic acids are in virtually everything we eat, anything that used to be organic or living, plant or animal. It has nucleic acids, and we don't need so many of them that it's really even worth listing on a nutritional label. They also don't contribute to the caloric content of our food. Now, lipids, proteins, and carbohydrates do. And so, if you're looking to limit your caloric intake, that is the amount of calories, the amount of energy that you bring in a day into your body, lipids, proteins, and carbohydrates all contribute to that number, whereas nucleic acids do not. But don't worry about nucleic acids. Again, they're abundant. We get as much as we need just by eating a normal diet. All right, so let's go through them. Carbohydrates. You also frequently hear people refer to them as carbs, quote unquote. Carbs. What's a carb? Well, it's an organic molecule that contains carbon and oxygen, as well as hydrogen. Simple carbohydrates are called sugars, and so some common ones are glucose, fructose, mannose, galactose, and so on. Um, Glucose is the most abundant sugar, it's the most common sugar, and it's the most important sugar. Whenever you bring fructose or galactose into your body in your diet, whether you're getting galactose from milk or fructose from fruits or uh, table sugar, um, they have to be converted into glucose before your body can use them. Before your body can use them, they all have to be converted into glucose. So, glucose really is the main sugar, the most important one. Glucose is also known as dextrose, and the difference between them is not significant for our purposes. You know, there's a definitional difference, but dextrose is pretty much glucose. And if you've ever worked in a healthcare setting, you may have heard of dextrose 50 or D50. It's a sugar solution that paramedics, EMTs carry on them. If you go into a diabetic coma, or sorry, well, not exactly a coma. If you are diabetic and lose consciousness due to low blood sugar, they can treat you with D50, and typically people will wake up nearly instantaneously. All right, then we have disaccharides. Now, the prefix di means two, and then saccharide means sugar. So, disaccharides consist of two sugars. And an example of a disaccharide would be lactose, which, of course, you know is found in milk. Lactose is a disaccharide, and a disaccharide, just to take a step back, is two sugars that are chemically bonded together. Okay, and so in the case of lactose, that's one glucose molecule and one galactose molecule chemically bonded together. Okay, lactose is one glucose and one galactose bonded together. And we actually can't absorb disaccharides. And so in the gut, we have enzymes that are going to break down disaccharides into monosaccharides. Monosaccharides, again, are single sugars. Mono means one. All right. So we break down disaccharides into monosaccharides, and then we can absorb the monosaccharides, the glucose, the fructose, the mannose, the galactose. And anything other than glucose has to be converted into glucose before we can use it. Now, you are probably familiar with the condition called lactose intolerance, and something like 70% of adults in America are actually lactose intolerant to some degree. And the reason for that is that a long time ago, our ancestors stopped drinking milk at around the age of 5. Now, of course, culturally, we can say that's a little late to be drinking your mother's milk, age 5, but that's what they did. And at age 5, you stop producing the enzyme lactase, which breaks down lactose into glucose and galactose, allowing the body to then absorb those sugars. So you stop producing that enzyme, and that results in a condition called lactose intolerance. The large intestine is just full of bacteria, and these sugars have to pass through the small intestine where you get a chance to break them down and absorb them. And then after that, if you haven't absorbed them, they pass on to the large intestine. And the large intestine, again, is full of bacteria. And if you did not break down and absorb lactose, then that sugar gets passed on to the bacteria who will break it down. And as a result of them breaking down lactose, they're going to release gases like methane. Okay, and methane is the stinky part of farts. Um, it's also a potent greenhouse gas. Anyway, that's true. It's a more powerful greenhouse gas than carbon dioxide. Anyway, uh, methane gas being built up in the large intestine gives us that feeling of bloating and discomfort that's associated with um, lactose intolerance. Okay. Now, I say 70% of people are lactose intolerant, 30% of people, 30% of adults, are not lactose intolerant. So, how is that if our ancestors didn't drink milk, they stopped drinking milk, their mother's milk at age 5? Well, the mutation that allows people to continue producing the lactase enzyme occurred actually twice. It occurred once in Africa and once in Northern Europe. And so some African and some Northern European populations are lactose tolerant. And so if you are lactose intolerant, then you probably have some genetic background shared with those peoples. All right, good. Moving on, sugars are the primary energy source for cells. Their purpose is just raw, quick energy. They can be metabolized, that's broken down much more quickly than fats can. Now, gram for gram, pound for pound, we'll see that fats actually store way more energy than carbohydrates do. But carbohydrates are a store, I'm sorry, fats are a storage form of energy. We store energy long term in fats and we're slow to break it down. Carbohydrates, when you need energy minute to minute to keep your cells functioning, to keep you alive, you're going to turn to carbohydrates. All right, so glucose we've mentioned, chemically similar, identical really to dextrose. We've mentioned all this. One thing, I don't want to ask you to learn a whole lot of chemical formulas, but this one's important and interesting. So first of all, the chemical formula for glucose is C6H12O6. Easy to remember, right? CHO 6126. Also goes back to the name carbohydrates, contains carbon, oxygen, and hydrogen. Anyway, photosynthesis is the process of combining CO2. Of course, you know plants take in carbon dioxide, right? And they combine that with water and the sun's energy to form glucose. Okay? And of course, all energy on Earth comes from glucose and ultimately the sun. Uh, Plants will break down glucose for energy, and animals will break down glucose for energy. And you're going to get glucose just a little bit in the animals you eat and a whole bunch in the plants you eat. So all the energy on Earth ultimately goes back to glucose, which is made with help from the sun. Anyway, we get glucose and oxygen over here. That's worth pointing out. Of course, we know plants take in carbon dioxide and they let off oxygen, right? They combine that carbon dioxide with water and the sun's energy to form glucose and oxygen. Now, cellular, it says here metabolism, really it would be better to say cellular respiration, is the opposite process. Okay, here we take glucose and then oxygen. Of course, you know, people breathe in oxygen, right? Well, what do we do with that? We combine it with glucose. Um, that's oversimplifying a little bit, but we combine it with glucose, and then we break down glucose into carbon dioxide, water, and energy. So this is the exact opposite process where we get carbon dioxide, water, and energy gives us glucose and oxygen. Glucose and oxygen we convert into carbon dioxide, water, and energy. All right. I just think it's beautiful how the two reactions are the exact opposite of one another. All right, so we can use sugars for a lot of things. One of the videos you have to watch this week talk about combining sugars, combining carbohydrates, combining sugars into complex carbohydrates that are structural, like cellulose. Cellulose is a common structural uh, polysaccharide found in plant cell walls, and humans actually can't break it down. Certain animals, like cows and deer, can, but humans cannot. We don't have the right guts for it. Uh, yeah. So, interesting thing about cellulose. Wow, can't believe I forgot that word already. Interesting thing about cellulose. Let's take a step back and talk about some other complex carbohydrates that we can't break down. Uh, and disaccharides. So first up is we mentioned earlier lactose. and 70% of us can't break it down because we don't make the lactase enzyme. Well, somebody figured this out, and they made a pill called Lactaid, which contains the lactase enzyme. So if you're lactose intolerant and you're going to go out to an all-you-can-eat cheese event, you might pop a Lactaid pill in advance. That way, your gut is filled with lactase enzyme that'll break down the sugars and prevent that bloating. Beans. You've heard that old song in grade school, beans, beans, the magical fruit. The more you eat, the more you toot. Well, beans contain a sugar called raffinose, and raffinose can't be broken down in the human gut. Small amounts are fine, but large amounts will again lead to gas in the large intestine, bloating, and flatulence or farting. And then somebody came along and they developed a pill for that. You may have heard of Beano. Beano is a pill that contains the enzyme that breaks down raffinose so that we can absorb the sugars, the bacteria don't get them, and you don't get the bloating and the gas. Cellulose is the most abundant sugar on the planet. It's in all of the plants all over the world. And if somebody could just figure out a pill that would allow us to break down cellulose, we could go out and we could just start eating grass. I mean, forget working 40 hours a week, to pay rent and get groceries. Just go live in the woods, eat some bark. You'll be fine. Just that's $1 million, $1 billion idea if any of you are looking for one. Work up a pill that allows us to break down cellulose. All right. And moving on. Cellulose, I mentioned that's a structural polysaccharide found in plant walls. There are other purposes, long story short, there are other purposes for sugars. We can use them as signaling molecules on the surface of a cell. Here, that would be called an antigen, and an antigen identifies the cell type to the immune system and to other cells. And so when the immune system, when the white blood cells come along and they're trying to figure out whether whether this is my cell or a foreign cell from outside the body, whether this is bacteria, fungus, a transplanted cell, the white blood cells come along and they feel the surface of the cell and they're feeling the antigens on the surface of the cell. And I liken this to you can imagine a blind person feeling fruit. If you feel coarse hairs on the fruit, you kind of figure out that's a kiwi probably. You feel soft hairs, maybe it's a peach. You feel round, bumpy skin, it might be an orange you're feeling. And the immune system works in a similar way. It feels the antigens that are on the cell surface and it decides then this is one of my cells. Or if the antigens are not familiar to the white blood cell, it'll decide this is a foreign cell and destroy it. Invading microbes, though, this is a double-edged sword. Invading microbes, that's microbial life, bacteria, fungi, etc., viruses even. They come in and they can detect your antigens and they can say, I found my target. Time to deploy the weapons. Here's a stupid little schematic I drew a long time ago, trying to show the concept of antigens, all right? And so all of these blood types have an H antigen, which is kind of like a stick sticking out of the cell. Up here we have type A antigen represented by a box, type B antigen represented by a heart, and then type O, which is actually the absence of an antigen here. Type O is called type 0 in other countries, and that's maybe a better name because there's no antigen here. All right. And so if you have blood type A, your cells will have the A antigen sticking out. If you have blood type B, your cells will have the B antigen sticking out. And if you have blood type AB, then you will have both A and B antigens on the surface of your blood cells. If you have type O, of course, you're going to have the H antigen here, but no AB antigen. Okay. Now over here, I drew a dotted line to represent what it would look like if you had no H antigen. And this actually is a real blood type. It's called the Bombay blood type because it was discovered in Bombay. People with the Bombay blood type, they might have the genes for blood type A or blood type B or even blood type O, but when they take a blood test, they're always going to show up as O. And the reason for that is even if you're making the A antigen, even if you're making the B antigen, if you don't have an H antigen here, there's nothing to attach it to, and and so in the test it'll look like you have no antigens on your cell surface and you'll show up as blood type O. It's pretty rare. It's just one of those interesting little science factoids. I'm going to look up now. Do we have any questions so far? I feel like we've covered surface level, but some pretty complicated topics so far. So I would love to have some questions. I'm going to sit here for about a minute or so and wait to see what comes up. All right. Well, nothing so far. Let's move on, I guess. If you do have any questions, throw them up there anytime. So, moving on, the next macromolecule is the protein. And so the proteins are made up of subunits called amino acids. You may have heard of amino acids. There's certain energy drinks out there now. Rockstar X Durance, I think Bang and Rain also contain branched chain amino acids, which are just small little chunks of amino acids that you can easily break down and absorb. Every amino acid has a nitrogen head over here, and then a carboxyl tail. And I'm not going to ask you to remember the carboxyl group. That is what a carboxyl group is, just nitrogen head, carboxyl tail, and then there's a central carbon here. And attached to the central carbon is an R group. And R, we could say, stands for rest of the molecule. So this is an simplified schematic of what an amino acid looks like. They all have this nitrogenous head, carboxyl tail with a carbon here, and then a central carbon, and off the central carbon is the R group. Now, where they differ from one another, what makes them unique, is this R group. Okay, and so the R group can take a lot of different forms. There are about 20 amino acids. Some people disagree on whether it's 20, 21, or 22. For humans, most people agree it's 20 if you say 21 that we use, but it's just scientists splitting hairs. We might as well say 20 amino acids. And we combine these amino acids to make proteins. Here's the subunit, and if I want to start building a protein, I'm just going to add another amino acid onto the end of this one, and then I'll add another amino acid onto the end of that, then another amino acid onto the end of that, and then another amino acid onto the end of that. And by doing this, we start to build a long chain of amino acids. A short chain of amino acids is called a peptide, and as we continue to build the chain, we can get up to protein status. Proteins are long chains of amino acids, and they can actually be quite large. Now, proteins are kind of the workers of the cell. Almost all of the work that gets done in a cell gets done by a protein. Normally, when we think about protein, we're thinking exclusively about either muscle or meat. And that's kind of the wrong way to think about it. Of course, meat and muscle are made of protein, but meat is made of things other than protein. So is muscle. And then protein does so much else in the body. Every cell is full of protein, just not as much as maybe a muscle cell. All right. Good. In fact, the bulk of our organs is protein. Our tendons are protein. Our ligaments are protein. And then we have a class of protein called enzymes. And enzymes are chemical catalysts. They're proteins that act as a catalyst and they don't get used up in the reaction, but they do speed up the reaction. And so if you had two little things floating around in the water and eventually they could meet each other and combine into a new molecule, you got a little part A over here floating around and a little part B over here floating around, and then eventually they can combine to make some product. Enzymes can speed that process up greatly, and they do it because they're able to do it because they have binding sites. And so the binding site of an enzyme might hold on to part a different binding site might hold on to part B, and then they combine the two parts. And the example I always use when we talk about this is imagine you've got a toy factory. You could put a bunch of doll heads and doll bodies in a box and then shake that box up, and then you open it up after an hour, you're going to have a couple of doll heads that manage to find their way onto doll bodies. But a much faster, more efficient way to do things would to be have a worker reach into the box and combine heads with bodies. And so that's sort of what an enzyme's able to do. It's able to hold on to the two, we call them substrates, the two molecules that are going to be involved in a reaction, and then combines them so that the reaction can take place more quickly. Antibodies are made of protein. Antibodies are made of protein. They're produced by the immune system, specifically B cells, B lymphocytes, which are going to travel through the bloodstream. And if they recognize an antigen that is foreign, they recognize an antigen that is not one of your antigens, they will bind to that antigen. And so let's say the antigen's on the surface of a bacterial cell, you'll get antibodies clumping up all over the bacterial cell. And they will sort of mark that cell for the immune system, other white blood cells when they come along. And those white blood cells will recognize that the antibodies are marking this bacterium, and then they will destroy the bacterium. So antibodies are used to basically flag a cell for destruction. They can also directly attack cells, and in great enough number, if you clump up around a bacterium, you just totally clump up around the bacterium with antibodies, you prevent that bacterium from functioning. It can't interact with its environment because it's literally surrounded by antibodies. We also have complement proteins, which are pretty cool. When I was a student learning about complement proteins, I thought they were awesome. It felt so empowering to me. Because if you watch the news, it's like we're constantly at war with microbes. We're constantly at war with bacteria and viruses and fungi. Viruses technically aren't microbes because they're not really alive, but that's just splitting hairs again. Um, all right. It seems like we're constantly at war with them, and it's a war we're losing. Any day now, some pathogen's going to come along and wipe out humanity. And I found it so empowering to learn that my blood is full of proteins that kill bacteria. These complement proteins, if they came into contact with bacteria, will actually form a complex and basically just punch a hole in the side of the bacterium. just pop it like a balloon. They're pretty cool. Bacteria typically don't do very well when they get to the bloodstream. Most pathogens are destroyed by proteins in the bloodstream. If, however, a bacterium or fungus is able to get into the bloodstream and is not destroyed, it is very, very dangerous. That's a systemic infection that can be seriously fatal. But most of the time, bacteria and fungi, once they come into contact with the blood, they're just destroyed, and that's really really cool, I think. Structural proteins. So proteins give a cell its shape. We'll talk about, I think, next week, the cytoskeleton. That is the cell's skeleton, which, again, gives the cell its shape, allows it to change shape or move in the case of sperm cells. Um, these structural proteins. We also have centrioles, which are like giant protein anchors in the center of the cell. And the cytoskeleton actually binds to the centrioles and uses it like, again, like an anchoring point to pull the cell apart when cells divide. All right, let's keep moving. We also have channels. These channels are made of protein, and they're pretty cool. So here we have the cell membrane. It's a phospholipid bilayer. We'll talk about more in a second. But basically, it's what we call a semi-permeable barrier. Some things can get through, some things can't. For the things that can't get through, if we want to get them into the cell, we've got to devise a way for them to get in. And so here we have a channel. And the channel, when it's open, will allow, let's say, the green things to get into the cell. All right. When this channel opens up, it'll allow the green things to get into the cell. And this one over here, we'll say when it opens up, it allows the orange things to get out of the cell. All right. But without these channels, or when these channels are closed, the green things are stuck on the outside and the orange things are stuck on the inside. They can't get through this barrier. No, no quiz. Ah, good. Moving on. The next class are lipids, and lipids are not water soluble. Uh, some proteins are water soluble, some aren't. Carbohydrates in general are very water soluble. Lipids, on the other hand, are not water soluble, meaning they can't dissolve in water. An example of a lipid would be oils. And you, of course, know the old adage that oil and water don't mix. Have you ever tried it? You mix up oil and water, they're going to separate out. And that's because oil is made up of lipids, which cannot dissolve in water. So, what happens to lipids in water if you shake them up? Well, they form little droplets. They would rather be surrounded by other lipids than water. And so they'll form little droplets and kind of sequester themselves, separate themselves off from the rest of the solution, from the water. All right, and so one of the most common lipids is fat. And we start over here. Let's point out this portion in peach color. All right, that's a fatty acid. All right. You can see here there's one, two, three fatty acids. Now, the fatty acids are of different lengths. You can notice that right away. And then this one is not straight, it's a little bit crooked. It kinks right here, it's a little bit crooked. All right, these are three fatty acids bound to a glycerol molecule. So, three fatty acids and a glycerol make a triglyceride. Triglycerides are commonly found in animal sources, so animal products like milk, eggs, of course, meat are all going to contain a lot of triglycerides. And they're pretty rare in plants, the triglyceride. Um, all right, moving on. What else can we say here? Mm, I'll just reiterate, I guess, that fats are the stored form of energy. Again, they're stored long term. It is slow breaking down fats. Now, fats do contain per gram or per pound more energy than uh, carbohydrates do. Um, but it is slower to break them down. It looks like we got a question. Hi, Marissa. Yes, you can watch it after. The same link that brought you here will allow you to watch the video once it's complete. Thank you for the question. All right, so good, good, good. Moving on. There's something I want to say here, but I want to. Okay, here it is. Uh, Saturated versus unsaturated fats. Let's talk about these. Saturated fats are saturated with hydrogen. Okay, this is a saturated fatty acid. You can see it's a straight chain, straight line here, and all of the carbons have hydrogens. Okay. Now, in an unsaturated fatty acid, not all of the carbons are saturated with hydrogen. And so, what's going to happen? If these carbons can't get a hydrogen, they're going to bond to each other. Same thing happens down here. And if these two carbons bond to each other, they hold really tightly onto each other, and that causes them to kink the chain. When these two carbons pull each other closer, that changes the shape. It kinks the chain of carbons. Okay. Um, and so saturated fatty acids again are linear, and unsaturated fatty acids have this kink because of the double bond between carbons. Examples of saturated fats are things like butter, things that are solid at room temperature, that is, lipids that are solid at room temperature, such as butter. Now, lipids that are liquid at room temperature are typically made up of unsaturated fats, and that would be things like oils, like olive oil is full of unsaturated fat. Unsaturated fat tends to be a little bit more heart healthy than saturated fats. Between the two, you should probably limit saturated fats more than unsaturated fats. We can talk also about trans fats. That was a big thing a number of years ago. Trans fats are being eliminated from products all across the country, all across the world now. You don't see them as often. Trans fats were a big thing, one, because they didn't have to be reported on labels, and two, because they were unsaturated fatty acids that behaved like saturated fatty acids. They found a way to get the unsaturated fatty acid to stick out straight. And so what that meant is that you could make things like butter, solids, um, solid lipids at room temperature that were actually made of unsaturated fatty acids and um, oh, sorry, the dog just came in. uh, Unsaturated fatty acids that behave like saturated fatty acids. And the body actually didn't know what to do with them. There are all kinds of strange health consequences. All right. Yeah, due to that straight stick shape of the saturated fatty acids, they tend to stack more easily. If we go back a second, you can see this straight chain here would allow fatty acids to stack one on top of the other more efficiently. Unsaturated fatty acids have that kink, which means they don't stack as well, and so it's harder to form something like a solid. That's why you get the liquid oils. Omega fatty acids are also something you hear about periodically. Omega 3 fatty acids are commonly found in fish. Omega 6 fatty acids are commonly found in things like flaxseed. And what this means, omega, the Greek letter omega, means the end. You've heard that phrase, I'm the alpha and the omega, I am the beginning and the end. And so here, omega, yes, remember, means end. Omega 3 refers to the third carbon from the end. That's where we see a double bond and is in omega-3 fatty acids, third carbon from the end. Omega-6 fatty acids, we see a double bond between carbons at the sixth carbon from the end of the chain. And studies show that omega-3 and omega-6 fatty acids can improve cognition, that's thinking, especially in children. It's a brain food. Now, moving on, we've got another class of lipid called phospholipids. All right, and so phospholipids have two fatty acid tails and then a phosphate head. Eh, Excuse me. And the phosphate head is negatively charged, but the tails are neutral. Now, water has a little bit of a charge itself. And so, what that means is that if you add a phospholipid to water, okay, the head, which is negatively charged, will be attracted to the water. The tail, which is neutral, we can see these little sticks down here, those are the tails. The tail is going to be, we say, hydrophobic. It's going to be afraid of water and want to get away from it. And so if you add a bunch of phospholipids into water, what they will do is automatically orient themselves so that the head, which is charged, faces the charged water. And the tail, which is neutral, is going to face other tails, which are also neutral. Okay, this is the most energetically favorable formation for phospholipids. And so if you add these phospholipids to water, shake them up, these membranes are actually going to form all on their own. Now, this is a double layered membrane. There's one layer, there's a second layer. Okay, and so we call this a phospholipid bilayer. Now, the plasma membrane which surrounds cells is going to be made up of a phospholipid bilayer. That's two layers here made up of phospholipids, with the phosphate heads facing the water outside the cell or the water inside the cell, and then the tails facing each other. All right, now embedded in the phospholipid bilayer, embedded in the membrane, we're also going to find a number of proteins. And these proteins serve important purposes. This one right here is a channel. We talked about channels earlier. They allow substances through the membrane. Over here we have not phospholipids, glycoproteins, where you have sugars bonded to proteins. And these will serve as cell markers, again, identifying the cell to other cells. All right. Anything else here? So let's talk about the nature of the phospholipid bilayer for a second then. This zone in the middle, all right, it's hydrophobic. It's full of phospholipid tails, which are neutral, they're water-fearing, they're hydrophobic. And so what can get through this membrane? Okay, what can get into the cell from outside? And what can get outside of the cell from the inside? All right. And that's going to be hydrophobic substances, or in other words, lipid soluble substances. Things that tend to be small and neutral, they have a neutral charge or no charge, they're going to be able to get through the membrane. And so this includes things like O2, CO2, they're small, they're neutral, they can easily get through the membrane. Alcohol, that is ethanol, drinking alcohol, is small and mostly neutral and able to get easily through the plasma membrane, no problem. Other things are not going to be able to get through, and so we have sodium ions, which are positively charged. They can't get through a neutral hydrophobic zone, and so they have to go through a protein channel to get into or out of the cell. Potassium ions are positively charged. They have to go through a protein channel. Okay. Now, those are small charged things. They have to go through a channel. There's going to be a process called endocytosis, where we form a little bubble in the membrane that surrounds big things and brings them into the cell. That's how we get big things in. Proteins are way too big, even if they were neutral, way too big to pass through this this membrane here. And so we would need to use endocytosis to bring in big proteins. All right. Before we move on to nucleic acids, I'm going to pause for questions and check on the dog. All right, let me know if there's anything you're wondering about. Now's your chance. All right, well, I'm still not getting anything from you guys. I guess we'll move on. Again, feel free to type it in anytime. Our next group up, and the last group actually, are the nucleic acids. And the nucleic acids you may have heard of before, they are DNA and RNA. DNA stands for deoxyribonucleic acid, and RNA stands for ribonucleic acid. And what's the difference between the two, RNA and DNA? Well, as you might guess from the name, DNA is deoxyribonucleic acid versus ribonucleic acid. We've lost an oxygen in the DNA. And so if you look here, the RNA has an oxygen at this position, and you don't need to remember it, but this is the 2' carbon. There's an oxygen bound to it. In RNA, over in DNA, that oxygen is missing, so this is deoxyribonucleic acid. And it may not seem like one oxygen atom would make that big of a difference, but it actually does make RNA less stable and DNA, lacking the oxygen here, more stable. All right. This is something that's not necessarily true. You won't always make, not universally true, I mean, you won't always make a molecule more stable by removing an oxygen. It just happens to be true in this case. And so DNA is the form of nucleic acid that we use to store genetic information long term. The sequence of nucleotides, by the way, nucleotides make up nucleic acids. The sequence of nucleotides that you have when you're born will stay mostly unchanged throughout the course of your life. And then 50% of that sequence is going to wind up in your offspring. So 50% of the DNA that you had when you were born will someday wind up in your child. All right, 50% of that sequence will wind up in the child. The other 50%, of course, comes from your partner. Good. So nucleic acids are chains of nucleotides. Here we see a nucleotide 1, 2, 3. Over here we have another 1, 2, 3. Okay. These are chains of nucleotides. Now there are 4 nucleotides in DNA and 4 in RNA, and they're almost the same. So the nucleotides in DNA are A, T, G, and C. We just simplify them to the letters most of the time, A, T, G, and C. That stands for adenine, thymine, guanine, and cytosine. The mnemonic I always use and that I tell students to use is at Gotham City. This also reminds me that A binds to T and then G binds to C. At Gotham City, ATGC, A bonds to T, G binds to C. Helps me remember the pairing rules. Now, the names of the nucleotides in RNA are similar, but they're AUGC. The thymine is replaced with uracil in RNA. So those are the two big differences between DNA and RNA. DNA lacks an oxygen. This nucleotide lacks an oxygen. This nucleotide lacks an oxygen. This nucleotide is without an oxygen at this position. And then the nucleotide thymine in DNA is replaced with uracil in RNA. Now, we mentioned DNA is the long term stable form of nucleic acids. The long term storage of genetic information is accomplished with DNA. What is RNA then? RNA is a short term form of DNA. Mostly in introductory classes, we talk about mRNA, which is messenger RNA. And so messenger RNA is like a little message, a little short transcript that was copied out of the DNA and it was copied in RNA. And then we can send that little copy off to another part of the cell to be turned into a protein. So we mentioned the four nucleotides in DNA: adenine, guanine, cytosine, thymine. They're all identical except for this nitrogenous base over here. The sugar part of the nucleotide is the same. The phosphate part of the nucleotide is the same for all of them. Sugar, phosphate, sugar, phosphate, sugar, phosphate. But over here, the nitrogenous base is what's different. Adenine here, guanine, thymine, cytosine here. We should also say that for DNA, and actually RNA too, there's a sugar phosphate backbone. There's a phosphate sugar, phosphate sugar, phosphate sugar, phosphate sugar. We call that the sugar phosphate backbone. In the center of DNA, that's where we find the nitrogenous bases here, the A, the T, the G, the C. Remember, of course, A binds to T, G binds to C. One more thing we should mention, one more difference between DNA and RNA we should mention is that RNA is usually single-stranded, meaning there's usually one strand of RNA. DNA is always double-stranded. We can separate the two strands briefly, but for the most part, it's always double-stranded. And so what we're seeing in this image here are two DNA strands. Here's one DNA strand, and here's the other one that's bound to it. And so an adenine on one DNA strand binds to a thymine on the other. A guanine on one DNA strand binds to a cytosine on the other. A thymine on one DNA strand binds to an adenine on the other. Okay? And so you can see that it's important that these pair up. All right, now again, I mentioned the most common, well, the most commonly discussed form of RNA is mRNA or messenger RNA. Now, how do we turn a gene into a protein, right? So let's go back a step further. What is a gene even? You hear so much about genes. What is a gene? A gene is a set of instructions on how to make a protein. For the most part, that's true. A gene is a list of instructions on how to make a protein. Strictly speaking, it's a list of which amino acids to include and in what order to make a protein. And so if we take this gene and copy it, well, let's take a step back. Think about a cookbook. A cookbook is full of recipes. Now, what is a recipe? A recipe is a set of instructions on how to make food. Let's say a pie. It's a set of instructions on how to make, let's say, a pie. Um, and so we can copy that recipe, okay? And if we copy that recipe, if we scan it in and print it out, if we copy it at a copying machine, what we're going to get is the recipe printed up on a page. Now, this is a cheap page. It's disposable. It's not as nice as the glossy page that was in the cookbook, but it's still got the recipe. It's still got the same basic information. That's good enough. Now, what can we do with that recipe? We can hand it off to our friend, and he or she can take that recipe home and make a pie with it. It's kind of the same idea, similar idea anyway, with DNA and messenger RNA. So a gene is a set of instructions on how to make a protein. All right. And then we're going to copy that gene. Now, we're not going to copy that gene in DNA. We're going to copy that gene in RNA, which is sort of a cheaper, disposable form of DNA, right? And then we send this mRNA, this messenger RNA, off to something called a ribosome. And that ribosome is going to read the recipe and then start building a protein. Okay. All right. Now, the process of copying the gene into RNA is called transcription, and that's where we're just transcribing it. The word transcribe literally means to copy by hand. And so we are copying something from DNA to RNA. We're copying something from the language of nucleotides into another form that's written in the language of nucleotides. Now, there's another process called translation, and that's where we're actually going to take the mRNA at the ribosome will read it, and then translate it into the language of proteins, which is amino acids. All right, so that is it for the main portion of the lecture. We're not done yet. Don't hang up. But do we have any questions so far? Please give me one. Just one. I'm begging you guys. This picture, by the way, uh, it's one of my favorite memes of all time. These slides came from an old lecture I used to give years ago um, at another college, but I just wanted to share this small section of the slides because it kind of fit into what we were talking about. All right, so go ahead and post your questions up there. I'm going to move on and talk about something else. Oops. New window. Let's go to mypath.kctcs.edu. Go to Blackboard. Well, thank you, Darian. At least for letting me know you're still here. I tell you what, while I'm pulling this up, why don't you guys let me know? Do you think? Let me know your opinion. Do you think we're spending too much time talking about really basic stuff, or do you think we're going way too fast over seriously complex stuff? Or is it somewhere in between? What do you guys think? Just let me know. And it's not going to hurt my feelings. I seriously take your input into consideration. I'm going to go ahead and pull up the thing I wanted to talk about. All right, so let's go ahead and talk about the learning assignment for this week, the learning module. It'll look differently for you guys, but this is basically the order of stuff. The recipe for life is the first video. I found it pretty entertaining. It's meant to kind of open your mind to some things. Not super informational, but definitely worth a watch. Up here, number 2, we have Chapter 2, The Chemical Basis of Life, your Learn Smart assignment. Now, of course, you can also access these through the McGraw-Hill Connect and or alternate McGraw-Hill links on the left. But if you want to do them as part of the learning module, you just come on through. They're right here. Second video, this is Crash Course Biology number 3, You Are What You Eat. it's a good video. Their videos are always good. This is one of their earlier videos, so maybe a little low budget and unprepared, but it's good. Then chapter 3, we have the Connect assignment here again. Two Connect assignments this week, chapter 2 and chapter 3. And then we have the discussion board, and you can click here to open the discussion board. It is called You Are What You Eat. And so the prompt is written down here. I'll go ahead and read it to you guys in case you can't see it. But basically, I start with the story. My sister is typically a very fit, health conscious person, but one day in college, she went to Baskin Robbins and she ordered the Heath Bar Shake. In fact, it was so good, she ordered another. And when she got home that day, she looked up the nutritional information for the drink and she was shocked to see that one shake actually contained enough calories for an entire day for an adult male. In fact, this drink has been labeled the unhealthiest drink in America by Men's Health magazine, and she drank two of them in one sitting. That's 2 days worth of calories for an adult male. Uh, and she's a small female. All right, so here's the question for the week. We would like to get 250 words at least. That's a minimum from you guys. And then we'd like to get you to post on two other people's pages, 100 words per post there when you're responding to other people. So the question, how often do you order meals without knowing the exact nutritional content? Now, when you go into most restaurants today, you're going to see a calorie count next to the price. Most chain restaurants today will have that. Um, but even that calorie count doesn't give you all the information you might need. So if you looked at the nutritional information, what were you looking for? Are you concerned about carbohydrates, fats, whether the fats are saturated or unsaturated, cholesterol? Are you worried about sodium? Then in parentheses, salt, because sodium is a constituent part of salt. That's where most of our sodium comes from. So please do the following. After thinking about and answering those questions, let's go to myfitnesspal.com. And I don't want you guys to see my sign in information, so I'm going to go to Be Right Back. Okay, come on. What? Sorry, I'm having technical issues here, guys. I must have clicked sign up. Alright, just going to log in with Facebook. Forget this. And so go there, create an account, myfitnesspal.com, if you don't have one already. Let me see here. Reports. I usually use the app. I'm actually having a hard time finding nutrition on here. Here it is. Okay, I'm going to switch back. You guys see me? Okay, great. So go to myfitnesspal.com, create an account. It's going to ask you all kinds of personal information. Not a whole lot, honestly. It's a pretty fast process. And then over here, you'll get your, sorry, that was home, and then I believe goals. Yeah, click that. And that's going to give you your daily information. Now, you can actually get all of this a lot easier on the app. The website's harder to use than the app is for some reason, but here it'll tell you what your daily goal is with calories if you want to lose or gain a certain amount of weight, how many carbohydrates you should be taking in a day. For me, that's 242 grams, no more. 40% of total calories. Fat, 67 grams. That's 25% of total calories. Um, Protein, 212 grams is the target. And I don't know if you ever tried to do that. It is hard to get 212 grams of protein in. 35% of the total caloric intake for the day would be protein. Hard to do. Hard to do. And then over here, it tells you what your goals are for the micronutrients and actually some of the macronutrients under micronutrients. Your saturated fat, for me, do not exceed 27 grams out of the 67-gram goal. All right. Polyunsaturated and monounsaturated. It says zero, not because you can't have those things, but because there's no daily recommended allowance for them. There's no number to put there, basically. Now, trans fat is zero, and you should definitely not get any trans fat in if you can help it. Cholesterol, you'll want to keep under 300 milligrams. I will. Anyway, this is just an example of what the numbers could look like. Your numbers will be different. Okay. And so what I want you to do is go ahead, go over here, create an account. Okay. Enter your information and you'll get personalized nutritional recommendations and then enter the food that you ate today. All right. And so did you exceed the values for daily calories, carbohydrates, fats, protein? Are you surprised by this? I'll tell you, there was one day where I was entering my information, and actually, I normally have next to no cholesterol in my diet, and I'm pretty proud of that. Usually, pretty much zero. And one day, I'm looking at my nutrition, and it says I've got 3 times the daily allowance for cholesterol, and my mind's blown. And I'm looking through my foods. What did I eat? And that morning, I'd had eggs. Eggs are rich in cholesterol. So these surprises do pop up. What kind of changes do you think you can make to accomplish your personal health goals? Now, whatever they are, that doesn't have to be losing weight. For some people, it might even be gaining weight, um, whether that's fat or muscle. So whatever your personal health goals are, maybe your personal health goal is just lowering your sodium so you can lower your blood pressure. All right, so this is what we want you to talk about. This is what we want you to do. Go ahead and click here. You can go over to the discussion board and click create thread. I'm going to test this real quick just to make sure you guys can post. Discussion board week 2 and create thread. That's where you'll want to click right there. Create your thread. All right, tell us about it. Tell us about your day. All right. So that's it. That's all I wanted to talk about. If you guys maybe in between, that's good. Uh, If you guys have any comments, feel free to email me anytime. You have any questions, you can shoot them at me now or you can email them to me again anytime. This semester, I have been just stellar about responding to emails. I don't think anybody's had to wait longer than 24 hours. Um, so I hope to keep that up. That's my personal goal, is to stay on top of emails. And there's no question too stupid. That's a joke. There are no stupid questions. Ask anything if you're not confused. It's better you do it early too, and I'll try and help you. Remember though, do send screenshots. That helps me out so much. It really speeds things up, and then I can get more emails answered, and then someday uh, get back to hobbies or see my family or something. All right. Well, thank you for tuning in. You guys have a good week, and let me know if there's anything you need. You too, Darian. And actually, I'm just now seeing comments over there. Thank you, by the way. Um, okay. Candace thinks we're moving fast. Biology and math are not really my thing, though, so it could be a personal thing. This is an introductory course, and it's not supposed to be impossible. The readings are going to be difficult. The Connect assignments are going to be kind of difficult. although there's really no punishment for getting things wrong. You just have to answer another question. Um, so yeah, we're not aiming to the exams might be just a little hard, but that's not my goal. Uh, so I will try and slow down a little bit. Um, yeah. Okay. Okay. So I'll try and keep that in mind in the future. Thank you guys again. Have a good night. And remember, you can always email me.